Welcome everyone, and thank you for attending today's Parasoft presentation on Mastering Aviation Safety and Cybersecurity, DO-178C and DO-326A. My name is Ricardo Camacho, Director of Software Safety and Security at Parasoft. Now, this is going to be a very educational presentation on satisfying the objectives defined by these critical standards in the aerospace industry. But before we get started, let's go through some housekeeping. First, everyone's microphone has been muted. However, if you have questions, please enter them into the questions dialog box at any time. We have someone available to address them at all times, plus we will have a Q&A session at the end of the presentation. This webinar is also being recorded and will be made available typically within 8 to maybe less than that hours after the webinar is over. All right, let's take a look at the agenda. On the agenda, I'm going to provide a high-level overview of each of the objectives or sections of Functional Safety Standard DO-178C, and I will dive a little bit deeper into Section 6 of the standard, since it pertains to testing to requirements and test verification, which Parasoft provides powerful solutions for. Then similarly, I'll be touching Security Standard DO-326A, the key objectives, particularly on the threat analysis. I'll also cover how these two standards live within the same software development process, and I'll very quickly show you an infographic on our powerful testing solutions, and then take you to a quick review site where you can hear it directly from our prospects and customers on Parasoft C++ test. Then we will finish it up with Q&A. All right, so let's get started. We will start with a little history. The Radio Technical Committee for Aeronautics, RTC, was founded back in 1935. They are an independent standard development organization and serve as a basis for government certification of equipment used by the tens of thousands of aircraft flying daily throughout the world's airspace. RTCA is a private, not-for-profit corporation which works closely with the Federal Aviation Administration, FAA, and other industry experts from the US and around the world, such as the EuroK working group, to help develop this comprehensive and contemporary aviation standard. The original DO-178 standard was released back in 1982. However, it was considered not very useful, then quickly followed revision DO-178A, published in 1985. This revision focused more on modern software engineering principles, verification practices, and introduced a correlation between critical failure conditions, level numbers 1, 2, and 3, level 1 being the strictest. You may know it better today as Development Assurance Level, or DAL. Then in December of 1992, revision DO-178B was released, which shifted from a how-to type of document to a what-to type of document. So it put a big focus on objectives that your software process needs to satisfy in order to reach compliance and ultimately certification. Another noticeable change was the critical failure condition, or DAL, which grew to 5 software levels and changed to letters from A to E, A being the most stringent and E having no safety requirement. Also, testing your requirements is strongly emphasized. You don't look at the code to create your test cases, you look at your requirements. And it's backed by structural code coverage to ensure that you have covered everything. Now, DO-178B also incorporated bidirectional traceability of requirements through design, test cases, and down to the code to show all the requirements that have been implemented. And the starter of having tools qualification for use was also introduced. Today we are at revision DO-178C, which was released in January of 2012, and this revision will be the focus of this presentation. You also see in this slide the European equivalent from EuroK. This is because the standard has been a continuous joint effort between RTCA and EuroK. Now, DO-178C made a lot of clarifications to remove imprecise wording around DO-178B. But the major adoption brought forward was a modular approach to supplemental guidance documents. For example, you now have DO-326A. DO-326A is referred to as the cyber version of DO-178 because the approach in addressing cybersecurity overlaps with much of what is done for safety. So if you've been building software systems that are safe, incorporating security will be somewhat intuitive. You now have DO-330, which addresses software tool qualification, DO-331 for model-based development, DO-332 for object-oriented software, and DO-333 for formal methods to complement your testing. Now, if you hear of DO-248C, it is a supportive documentation for DO-178C containing clarifications and information on rationale for each DO-178C objectives. Additionally, standard DO-278A is based off of DO-178C, and it's specifically for ground systems such as air traffic control systems. However, standards like DO-178C are not just being used for avionics. The FAA and military have adopted it for use on non-avionics systems. For example, about 8 years ago, I helped test the arresting gear of the General Ford aircraft carrier to DO-178B, Level B. The arresting gear is the cable that stops the aircraft during landing. Not in avionics systems, but DO-178 was used. Now, Section 2 discusses the system's requirement allocation to software, where the software system requirements are initially developed from the system operational requirements or customer requirements, and how this information flows into the software lifecycle. One very important part of Section 2 is the software level classification or design assurance level determination that needs to be made. Catastrophic results would be failure to flight control software where the plane would go down and lives would be lost. This would be classified as software level A. Hazardous would be a step down, so serious or fatal injury to a relatively small number of occupants. This would be software level B. And classification continues to go down to level E, where there is no safety concern if software failure were to occur. Now, the other side of this classification is that with each increased level as you go from E to level A, there is an increased number of objectives that needs to be met. Section 3 discusses the aspect of the software lifecycle process. You are not told what development methodology to use, but to consider things like the system's functionality to be implemented, the complexity, the software size, the hardware availability, and other attributes. Now, here is the standards example of 4 different development sequences that may be used between different software components. So you can actually apply different development methodologies within the development of the system under design. But again, it's up to you to decide on what works best for your project. Whatever development methodology you choose, the key is that the standards objectives that must be met are not obstructed by the process. Section 4 discusses the objectives and activities of the software planning process, where the production of software plans take place. Table A-1 lays it out for you, so let's take a look at that table. You can see the 7 objectives on the left-hand side. Documents capturing plans need to be put in place. You have the output documents like the PSAC, SDP, SVP, SEM, and SQA, and the standards that are going to be followed for requirements, design, coding, and software verification. In the middle, you can see the software levels and which objectives need to be met based on assigned software levels, A through D. Lots of activity happens in Section 5. It starts with the development of your high-level requirements. The inputs are the system-level requirements, the hardware interface, and the system architecture. High-level requirements are then decomposed during the design phase, and low-level requirements are developed. Then source code is developed from the low-level requirements where coding standards are applied. Then there is some integration activities and traceability. Traceability is crucial to DO-178C, and the depth of traceability varies based on the DAL or software level. So let's step through this very important aspect of traceability. If we look at the traceability that is required for DO-178C level D, we don't care about how the software has been developed, and as such, there is no need to have any traceability to the source code or software architecture. As can be seen here, we just need to trace from the system software requirements to the high-level requirements, and then to the test cases, test procedures, and test results. For levels B and C, how the source code has been developed becomes important, and so we now need to ensure bi-directional traceability from the high-level requirements to the low-level requirements, and then to the source code. Finally, for level A projects, there is the need to trace not just down to the source code, but since the source code is compiled into executable object code, then traceability is also required down to the executable object code. So we have thus far described the requirements management that happens on the left-hand side of the V process model, which I'm sure you're all aware of. And the next section of the standard, section 6, covers the right side of the V model. The purpose of the software verification process is to detect, report, and remove the errors that may have been introduced during the software development process. Now, the standard uses the term verification instead of just test, because testing alone cannot show the absence of errors. So verification is a combination of reviews, analysis, and tests. There are many verification objectives defined in section 6, and they have been captured in tables A3 through A7 of the standard. Table A3 shows us the verification objectives for the high-level requirements defined during the software requirements process. As we go through these tables, note that we will be going through different verification levels of abstraction because we are testing to requirements which themselves are at different levels of abstraction or decomposition. Table 4 shows us the verification objectives for the low-level requirements defined during the design phase. Table 5 shows us the verification objectives for the source code and integration process. Table 6 shows us the verification objectives placed on the executable object code or assembly code. So as I mentioned before, this is verification at a much lower level of abstraction. Table A7 shows us the objectives for the verification of the verification process results. This is done through confirmation of code coverage during test execution, reviews, and analysis. And the code coverage objectives can be at the statement, branch, modified condition decision coverage, and at the object level. Coverage of data coupling and control coupling may also need to be achieved, but this is based on your software level, which includes traceability down to the source code as well. Section 7 discusses the objectives and activities of the software configuration management process. You need to have one. You need to be able to define and control configurations of the software through the software lifecycle, having baselines, versioning, change control, change review, protection against unauthorized changes, problem reporting, and quite a bit more. Tables 7-1 and table A8 of the standard list all of those objectives for you. Section 8 discusses the objectives and activities of the software quality assurance process. The process needs to provide assurance that the software plans and standards are developed, reviewed, and will meet compliance. For example, perform your own audits to ensure that deviations from the standard are detected, recorded, evaluated, tracked, and actually resolved, and that approved deviations are recorded as well. For certification, a conformity review should be performed to ensure that you have all your artifacts, reports, and evidence in place with approvals. Section 9 discusses the certification liaison process. For certification, you will want to work with a designated engineering representative, DER, who will evaluate for compliance and act in your behalf towards approval and recommend that the FAA approve your certification. Section 10 is provided for information purposes only regarding the certification process. It mentions the types of systems and equipment that the certification applies to, that certification authorities do not certify software as a unique standalone product. It has to be part of an airborne system or equipment. Also, the approval depends upon a successful demonstration or by review of the product. Section 11 discusses the data or documentation artifacts that are produced during the software lifecycle, and that the data be unambiguous, complete, verifiable, consistent, modifiable, and traceable. Also, that it be in various forms, electronic and printed. This refers to the artifacts produced during the software lifecycle. This includes the source code, the object code, the test cases, the results, the problem reports, including your plans, such as the plan for software aspects of certification, the software development plan, software verification plan, configuration management plan, software quality assurance plan, and many others. Section 12 discusses additional considerations regarding things like the use of previously developed software or already certified software for use on an alternate type of aircraft, or certified software where there is a change in the compiler or processor, and the list continues. But what stands out the most to me in Section 12 is the tool qualification and determination if tool qualification is needed. So if a tool is used that eliminates, reduces, or automates processes, you have to take into consideration whether the tool might introduce errors into the life cycle. You will need to determine if the tool being used needs to be qualified. Don't forget that there is the supplemental DO-330 software tool qualification considerations, where the objectives, activities, and guidance is provided. You can see the criteria listed on this slide and the table that maps the qualification level of the software level based on the criteria. TQL1 is the most rigorous level, and TQL5 is the least rigorous level. As the potential impact of the tool on the software lifecycle process increases, the TL rigor increases due to that potential impact. Vendors like Parasoft provide qualification kits that automate the qualification process, and this is because in DO-178C, the tool needs to be qualified for use on each specific system. What you need to be careful of is use of a tool that has never been qualified. The responsibility will fall on you to qualify it in order to have your system pass certification. So be real careful. So I want to put the key challenges in a nutshell for you, but be aware that some of these challenges only get triggered based on your DAL or software level requirement. You will definitely need to perform bidirectional requirements traceability. Make sure you have a solid requirements management solution in place. Make sure you know which compliance objectives you need to satisfy and document and mark them off as you go. Adopt a coding standard and make sure you comply to it. There is MISRA, CERT, perhaps you have your own, or perhaps you want to use a hybrid combinations of these standards. Make sure you perform and document your data control coupling analysis on your code if your DAL requires it. Also, validate on your hardware target. Remember, it's the system that is getting certified. Also, perform structural code coverage to ensure that you've tested all your requirements. Also, you may need to perform code coverage at the object or assembly code level. Use a tool that has been qualified in the past, and that there is a tool qualification kit available to automate the qualification process for you to use within your development ecosystem. Finally, have a compliance management plan and expert, DER, that can help you through the certification process. Okay, let's tie in security into the software lifecycle. Safety and security can be done in parallel as captured in this V diagram. One key difference between safety and security is that for safety, you need to perform a safety assessment, determine the failure that can occur and mitigate them. In security, you need to perform a security assessment to determine all your threats and vulnerabilities and mitigate them. These mitigations for safety and security become requirements that you need to decompose, build traceability, implement, verify, and validate. All right, anyways, let's start with a little history here on DO-326A. In 2006, EuroK formed a working group, 72 or WG72, and in 2007, our TCA formed Special Committee 216 or SC 216, both named Aeronautical Systems Security. And this began the process that yielded DO-326A. The equivalent in the European is ED-202A. The first section of DO-326 was published in 2010 called Airworthiness Process Specification, but it lacked information or content on security. It contained best practices as best understood at that time, since security had not been widely implemented in the industry. The current publication of the standard Airworthiness Security Process Specifications was put out in August of 2014, along with companion document DO-355. A key important or contributing element of the latest version of DO-326A is that it includes the focus of malicious intent, because just looking at incorporating security in the system leaves gaps that bad people can use for sabotage. So intentional and unintentional threat is considered. DO-326A is also a process document. That means it focuses on the what and not the how. So there are objectives defined to be satisfied in order to reach the goal of obtaining what is referred to as type certification. Also, guidance and recommendations on how we can keep avionics systems secure have been dispersed across several documents. There is DO-326A, or Europe's equivalent, ED-203A. It's titled Airworthiness Security Methods and Considerations. It is a companion document to be considered. It provides airworthiness security requirements throughout the stages of development, and it spells out details on risk assessments and objectives to be achieved. Now, another complementing document is Standard DO-355. It is titled Information Security Guidance for Continuing Airworthiness. It's a collection of supplementary requirements focused on operations and maintenance. The core of DO-326A is to establish the airworthiness security process. The term has been abbreviated, so you'll see AWSP as the acronym. And this standard is the top level guidance for attaining airworthiness security certification. As I mentioned, this certification is required by the FAA and EASA. And this is for general civil aviation, like fixed wing and prop aircraft, rotorcraft like helicopters, and this includes the engines and propellers. It's also important to note that current military aircraft is not addressed by DO-326A, though it's under consideration. This image captures the overview of the airworthiness security process. We don't have time to go into complete detail. I will also put focus on the life cycle phases, which are primarily captured in Chapter 3 of the standard, where I believe most of the importance in the standard is found. As you can see, steps 2, 3, 5, and 6 reference sections in Chapter 3. Now, starting at the top, you have steps 1 and 7, which express how to manage the actual certification process. There is a plan that needs to be put in place. It contains things like the risk assessment of the aircraft or system, which includes essential processes like assurance level assignment, security requirements capture, security requirements validation, and it serves as other inputs to further activities down the line. Also, this document has to be in agreement with the regulatory authority, because other supporting documents like the aircraft security scope definition, which captures the operational environment of the aircraft as it relates to security, may be required by the authority. This is to give you a sample visual of an aircraft environment when considering security. Other documents like the Preliminary Aircraft Security Risk Assessment captures all identified threats, conditions, scenarios, along with security risk assessment levels that may be needed. Or even a software design document may need to be included in the plan, so work it out again with your regulatory authority. Something that comes into play here is if there are just modifications being made to the system and not for certification. Anyway, evidence to support the plan or PSEC-AC document includes things like assigned security assurance level, results in the verification validation of requirements, and more are to be included in the plan, which is step 7. Step 2 is where you establish the scope, or in other words, identify the assets that are to be put in through the airworthiness security process. These will be the logical and or physical assets in development, but it's important to understand that it involves different levels of abstraction. For example, you can start by looking at things from the perspective of the aircraft and consider assets like external communication systems, the interactions that happen, including with off-board personnel. At a lower level of abstraction, you have to also consider the system and its internal assets. The system, the subsystems, the interface, the data, the file transfer, and much more, because these assets also need to ensure security. Step 3 is where you perform your security risk assessment. This is similar to how you evaluate and assign your design assurance level in safety. This is figure 3-2, which shows the workflow defined in determining the security risk assessment level. This is level of threat and severity. Chapter 3 goes into further details such as providing asset security attributes and threat conditions. Based on the security assessment level assigned, it affects the various verification validation methods to perform and assure that the asset is secure. This feeds into step 4. Step 4 is a decision gate. If there is a security risk, evidence of assessment and mitigation measures need to be produced, which feeds steps 5, 6, and 7. Step 5 is where security protection is implemented in the design, and step 6 measures the effectiveness of the security protection implemented. Steps 5 and 6 are given additional detail in this diagram. Additional security requirements are defined and architectural decisions are made in support of these high-level security requirements. And all of these requirements need to be satisfied and measured for effectiveness. This means testing. The results are what feeds actually step 7. Step 7 is where all evidence of activities and results is captured for certification purposes. So let's put these steps into something more concrete, something that we are more familiar with. This V process image is from the DO-326A standard, and it puts things in the context of security. It captures the phases of the software development process. And just like DO-178, it's up to you to select whichever development methodology, whether it's spiral, agile, waterfall, that best suits your team or project. On the left side of the V, we have the system engineering phases where you capture requirements. This is where step 2 in the DO-326A process comes into place. As you can see, you have abstraction levels of security requirements analysis that you need to consider, where requirements are identified and they also need to be decomposed. When I say requirements, these include the collection of regulatory as well as the stakeholder requirements, which we should all be very familiar with in performing our system engineering task. This process is very well defined in DO-178. The key difference here is that we are adding a security process which is well defined in DO-326A. So know that there is also a security risk assessment to be made. If the security assessment level requires threat mitigation, it must be designed into the system, and a test to verify the effectiveness of the solution against the threat must be defined. Now on the right side of the V, we perform the verification and validation of requirements. The security requirements, just like safety requirements, need to be evaluated through our verification and validation methods. The artifacts produced feeds into our compliance and certification needs. Now, DO-326A provides a list of E-enabled systems to consider, shown here, the list on the left-hand side. So you're going to have to do assessments on these and find out what the vulnerabilities are to consider. So assess your security threats and make sure to thoroughly test the effectiveness of the solutions that you've actually put in place. Now, I just want to communicate that Parasoft provides a comprehensive set of tools and test methods like static analysis, unit testing, on-target hardware testing, structural code coverage, UI testing, fuzz testing, API testing, and service virtualization, and actually quite a lot more. This is all in support of safety and security verification and validation of avionics. And our solutions seamlessly integrate within your modern CI pipelines. So we have integrations with Azure, GitLab, Jenkins, GitHub, and because it's all about satisfying and testing your requirements, we have integrations with Doors Next, JAMA, Codebeamer, Polarian, Jira, and others. Now, one last thing, instead of showing you one of our case studies on DO-178, I decided to show you something a little more real. This QR code will take you to SourceForge, a review site, actually the largest, most trusted destination for software discovery and software reviews on the web. So actually, let me take you there. Here you will find a review of C++ tests. You're actually going to find a demo video. Please watch it so you can see how C++ works. Lots of product details there. Also, you're going to find frequently asked questions. There's also a collection of features. And you can also see here some of the reviews. For example, there's an engineer here. Timothy, whoever that person is, software engineer, the best DO-178's on-target testing tool that they've tried. And you can see here what they actually wrote about this. So very interesting things. Tests are code rather than spreadsheets. We spend months evaluation of Parasoft's competitors, and before they actually got to us. Also talked about the DO-330 tool qualification kit, so that's available as well. And anyways, they're using CMake, they're using LinksOS 178, and another very important aspect here is it took weeks with other tools to get their code to properly be instrumented and extract coverage from the target hardware. So with Parasoft, it just took 16 hours across 2 work days, and they ran into very few issues. So there are, again, lots of reviews. You can see we perform very well, and this is actually rather recent. So nothing that's many, many years ago. So anyways, I'm going to let you guys navigate here, look at those reviews so you can get it from the horse's mouth. Okay, so let me jump back to the presentation and enable us for the live Q&A. Okay, but first, here's some call to actions that I want to show you. I provided a QR code to take you to our request a customer demo of our C++ test solutions. The center QR code will take you to a tour of our products, and to the right of that, you will go to our resources page where you can access lots of educational and informative content. There is also a fantastic DO-178 ebook that I highly recommend that you actually download. And don't forget to follow us on Twitter, LinkedIn, Facebook, or send us an email at info@parasoft.com if you happen to come up with any questions after the webinar. Okay, so let's go ahead and open up for Q&A. We got some questions. Let me go through this here. Let's see. First, what types of testing are emphasized under DO-178C's verification process? So DO-178C emphasizes various testing activities. However, requirements-based testing, this is the core of DO-178C verification. So you need to build test cases that are designed to verify that software functions meet high and low level requirements. So this ensures that each requirement is actually accurately implemented and functioning as intended. Nevertheless, you still need to perform static code analysis, structural code coverage, statement branch, MCDC, and testing down to the object code level for higher DALs, data and control flow coupling, integration testing, system testing, robustness testing, the actual on-target hardware testing, and actually much more. So these testing requirements are captured in the standard as objectives that you need to satisfy. Also, it's important to understand that the verification includes peer reviews and analysis, like looking for undecomposed requirements, any missing test cases, and documentation, as testing alone cannot confirm the absence of errors. And this is the same for DO-326A in cybersecurity. So we've got questions here. Why is it that a test tool cannot be certified by TÜV? So that's a good question. In avionics systems and for DO-178C, because of the tool itself, you have to ensure that it does not bring in any issues or any false information or anything like that. You actually have to qualify it within the development environment, within the development ecosystem. So having it certified by a third party, by say something like TÜV-SÜD, which their industries like automotive and medical and rail and so forth accept, for avionics systems, that's not enough. So you have to qualify the tool within the development environment. So with DO-178B and DO-326A defined for avionics, is common criteria certification relevant in avionics domain? Oops, hold on, let me scroll back up here. Somehow that moved. Is to define it before is common criteria certification relevant. So yeah, I mean, they both require certification. You have certification for safety and you have certification for security. Common criteria, we kind of went through that, the same process, the same defining what those requirements are to ensure safety and to ensure security, and you need to make sure you satisfy those. So which exact objectives of DO-178C does the qualification cover? For instance, is the data flow analysis qualified? So, I mean, so there are several objectives, and based on the DAL level. So if you have, say, DAL C, the objective says that you need to perform data coupling and control coupling. So data flow and control flow coupling. You have to do that. It's just those are the objectives that you need to do. I mean, yeah. So let's see, can we use FMEA for security? Well, no, but well, I mean, they both overlap, but no. FMEA is to perform your fault assessments. If a fault occurs or some piece of hardware fails, what do you need to do in order to ensure safety, or that the system recovers or it mitigates whatever issue it has for safety purposes. So no, FMEA is not for security. For security, there are actually frameworks out there that you may want to follow. There is NIST has several, ISO standard has several, MITRE has also several frameworks that kind of help you step through the security process. Look at the asset, where are the potential vulnerabilities and how you mitigate those. And so there's actually databases out there available from some of these institutions like NIST, where you can already look at and find what are the common vulnerabilities. So you don't have to kind of necessarily brainstorm a lot. You can actually go there. And so if you have a USB connection or you're using a particular protocol, there's a lot of that stuff already available for you. But what is the, okay, how can US government call about memory safe programming languages hit the certification process? Is this the case? This is related to safety critical applications. Yeah, I'm not sure exactly what to mean, but there are, I mean, when you write software, you know, when you especially in mil-aero, you're using C and C++, you're using Ada, you still need to make sure that you manage your memory properly. In pretty much all cases that I've looked at, you know, the software memory is pre-allocated, so you don't do dynamic allocation. So the new and the delete operations are overloaded. So you have to, no programming language is completely going to ensure that your memory, you're doing memory safe programming. I know there's Rust and stuff, but you still need to make sure that the code you write is safe and is secure. Yeah, there's a question here about, okay, that wasn't Indeed, but they said, do you cover DEL-A data flow analysis in your qualification kit? So one of the things that, and because there's another question here related to qualification kits, does Parasoft help with tool qualification for DO-178C? So yes, Parasoft supports tool qualification for DO-178C. DO-178C compliance requires that any tool automating processes impacting safety undergo a qualification process to verify it performs reliably in its intended environment. So Parasoft assists this by providing a tool qualification kit, which streamlines the qualification process. So the kit includes documentation, scripts, and automated tests that demonstrate the tool's reliability and alignment with DO-178C objectives. The evidence produced through this qualification kit demonstrates the tool's effectiveness and correctness, supporting its use in safety and security critical projects to meet DO-178C compliance requirements. So there, our tool qualification kit actually is going through some enhancements, and we are about to release, I think before the end of the year, a new, more enhanced, fully functional tool qualification kit. So, is MISRA-C an accepted standard for developing avionics systems? Yes, MISRA-C is. MISRA-C is the de facto coding standard for C, and of course you have MISRA-C++. What I would recommend is that MISRA actually came out with MISRA-C 2023 and MISRA-C++ 2023. So I would highly recommend the use of those two. Of course, you also have AUTOSAR C++ 14 in the automotive industry. I still recommend that they actually kind of use a combine of MISRA and AUTOSAR, but that's a whole different domain. Okay, actually, I don't see any more questions. Let me see, actually, there's one more here. Let's see, if your testing tool is updated, does it need to be requalified under DO-178C? So yes, if a tool is updated, it generally needs to be requalified under DO-178C to ensure the changes haven't impacted its reliability or compliance. Now, the extent of the requalification depends on the nature of the update. Minor bug fixes might only require partial requalification, focusing on verifying the specific changes, while major updates or new features typically call for a full requalification because they could introduce new risks. In either case, regression testing is used to confirm the existing capabilities, making sure that they remain unaffected. And again, Parasoft's tool qualification kit is designed to support both initial qualification and requalification, again, simplifying the process of ensuring compliance even when the tool is updated. And oops, I think that ends our presentation, folks. Thank you for attending. We have actually our next webinar, we're going to have a product launch happening real soon. So our next webinar will be on the new features and capabilities of the C++ test. And so I highly recommend, because there's some real cool stuff that's happening. We're integrating artificial intelligence into our static analysis tools. We're very innovative. And also don't forget that what I mentioned about Doors Next, C++ with Parasoft DTP support Doors Next, which is heavily used in the avionics industry. All right, well, thank you for attending. There's no more questions. Again, if you come up with any questions, please send us an email at using info@parasoft.com. All right, take care, folks. Bye-bye.